Our final lesson of this unit, and you guys have done a great job of working through this. And we start with the definition of a one-to-one function. So who can tell me about the operation that you learned yesterday? You learned about a new operation yesterday. What was it called? Yes.
Fog.
Fog?
I forgot what it was.
So it's the C. Composition. Thank you, Marissa. Way to go. Composition. Composition of functions, which we write something like this. So that is one operation that we learned. I told you we learned another one today. Function inverses. We're going to learn about that today. And in order for us to be able to discuss function inverses, we first must decide what it is to be one-to-one. And what it means to be one-to-one is this. See if this sounds familiar. A function is said to be one-to-one if every element of the domain corresponds to exactly one element of the range. Does that sound familiar? Because that's the definition of a function. A one-to-one function also says, and every element of the range corresponds to exactly one element of the domain. Every element of the domain corresponds to exactly one element of the range, and every element of the range corresponds to exactly one element of the domain. Okay. Good. In order for a function to be one-to-one, it must pass the horizontal line test. So let me show you what that means. Oh, good for you. She sees it. Okay. I'm going to draw a function in blue, and that function is one-to-one. And the reason why that function is one-to-one is because as I drag the horizontal, so I drag the horizontal line across it, the horizontal line always crosses it just once. See that? That means it's one-to-one. So I'll show you an example of not one-to-one. And that function g in red is not one-to-one. And the reason why is as I drag this horizontal line, notice many times it crosses how many times? Yeah, 3 times. And so I want you to understand what this means in connection with the definition. Notice that the line is at an output value. Okay, say an output of 4 or something. How many inputs correspond with that output? 1, 2, 3. See that? This output corresponds with 3 different inputs, and that makes it not one-to-one. So, in order for functions to have inverses, they must be one-to-one. So we're not going to be talking about the functions in red today. We're going to be talking just about the functions of blue. We good? All right. Very conceptual at the beginning of class. Then we get to examples, and that will help out. Function inverses. First of all, F inverse does not mean 1 over F. Do you see why people might want to write it that way? Yeah, we're used to seeing, if you see a negative, drop it to the denominator. That's not what we're talking about at all. Here's what we're talking about when we say a function inverse. It means that the domain becomes the range. It means that the range becomes the domain. Is the range the x or the y? The y is the domain, the x or the y. So what it means is the x's become the y's, and the y's become the x's. They switch places. They switch places. That's the best way to think about inverses for you right now. So let's try one of the most basic examples. And this will really help you understand what we're doing. I'm going to give myself a function, and it's going to be 3, 8. It's a very boring function. I hate to say boring. I like... okay, here we go. So, can somebody tell me what f of 3 is? 8. And you say that because if you have an x value of 3, that produces a y value of 8. Easy enough? Okay with that? All right, so what if I asked you f of 8? I don't see any coordinate up there that has an x value of 8, do you?
No.
So we don't know what f of 8 is. We don't have an x value of 8 anywhere up there. Agreed? So let's look at this. F inverse of 8. What happens in that situation is instead of this being an x value, this is a y value. It's saying if you have a y value of 8, what's the corresponding x?
3.
It is 3. So suppose I had f inverse of 3. Do you have any spot where you have a y value of 3?
No.
No. So we don't know that value at all. You can have a graphical representation. Graphically, they are reflected over the line y equals x. And this will be really cool. I'm going to show you a graph here. What coordinate is this? 1, 3. Everybody agreed? And so its inverse would be 3, 1. So if I plot those, can you tell that they're just reflected over y equals x? Which is interesting because, again, inverses are where we switch y and x, right? So now, the conceptual part sometimes we get frustrated with. It's not the part of math that we always connect with, but it's important. Let's go to some examples, and this will make sense for you because you like the algebra. That's what draws you to the math, and I get it. So here it says f of 2 is 3, f of 1 is 9, f of negative 3 is 8, and f of 4 is 5. It says that the function is 1 to 1. That means it has inverses. So find the following. F inverse of 8. Yep, that means for a y value of 8, what's the x value? F inverse of 3? It is 2. F inverse of 5? F inverse of 9. Look at that. Can you get those right on the test?
Yes.
Awesome. Look at how smart you are. Okay, let's try a slightly more challenging example. It says, given the function is 3x minus 8, find f inverse of 6. Does that mean I take the 6 and I plug in for x? No, because 6 is actually the y value. So I say 6 equals 3x minus 8. So for a y value of 6, can we find the x value? And we can. So we add the 8 and we get 14. We divide by 3 and we get 14 thirds is equal to x. Everybody good? All right. Remember, you can call me ugly, stupid, horrible teacher, worst person you've ever met in your life, but you cannot say, I don't tell you what you need to know for the test. If you say that, you are a liar. So, you have to know how to do this for the test. Find inverses for the following functions. We have the function f of x is 2x minus 5, or y is equal to 2x minus 5. I would like to find the inverse. What do you think I do to find the inverse? Switch x and y. Everybody okay with that?
Yep.
Now I just solve for y. Add 5. So x plus 5 is 2y. Then divide by 2, and you have x plus 5 over 2 is equal to y. If you would like to write 1/2 x plus 5 halves, that would be okay as well. That's it. You okay with that? We found an inverse. I'll show you this a couple times. I'll do it once right now. I love to go into my y equals, and I like to type in 2x minus 5. I also like to type in parentheses x plus 5. Or is that, yeah, x plus 5 divided by 2. And then I like to type in y is equal to x. I'm going to make that one bold. And notice that we will see both graphs. This is one way in which I check my answers because I don't like getting problems wrong. Does it look like one line is like the other line reflected over that? Notice the y-intercept of this one is 5. That means that the other one has a x-intercept of negative 5, right? This one has an x-intercept of 2.5. That means the other one has a y-intercept of 2.5. See how they switch? It's so nice. Okay, let's try a more difficult example. We've got y is equal to 2 minus x over 3x minus 4. So what's different is we have a fraction here, and we have multiple x's. If we switch that and we get x is equal to 2 minus y over 3y minus 4, how do you think I can solve for y? We're going to cross multiply here, and I get 3xy minus 4x is equal to 2 minus y. Is everybody okay with that? Okay, we're going to try to pull to something you learned at the beginning of the year. Usually helps at this time. I'm trying to solve for y, but I have two different y's. What do? Put them on the same side. Nice work. 3xy plus y equals 2 plus 4x. So you took everything that has a y and you put it on the left side, and everything that doesn't have a y, you put that on the right side. What are you going to do to isolate the y? Factor out the y. So that's a trick that we did earlier this year. Some of you did it correctly on the test. Some of you did not. I've isolated the y. What do I do now? So y is equal to 2 plus 4x divided by 3x plus 1. The difference was earlier this year you weren't solving for y. You were solving for x. Well, now you're solving for y. So can you see that people will make that mistake on the test? Yeah. What's that? You mean you like this more than the word problems?
Yeah.
No. Trust me, the other word problems we see throughout the year, they will be better because of the work you put in now. Trust me. Trust me.
I just don't. There's more word problems.
Yeah, I mean, normally on a given year, it's every couple of units we got to investigate problems. So we won't do quite as much in previous years, but we got to do some, otherwise we'll just continue to be behind for years to come. Flip it over. Last page of the notes. We're going to do 4 more examples. We'll be done. I'm going to switch this problem. I don't like the one that I created before. Not happy with it. So I'm just going to switch it. That's what happens when you're a math teacher. You can do what you want. Yep. All right. So I'm going to find this inverse. So I have x is equal to y cubed plus 6. What do? So I got x minus 6 is equal to y cubed. Cube root both sides. X raised to the third plus 6. And then if you want to see the cubed root, press math. You could get to your cubed root one by pressing 4. X minus 6. And then we've got, yeah, that's it. And love this graph. This is kind of fun. Wait, can you tell graphically that they are inverses? Again, so for part of me, that's the beauty of math. That every single time I do a problem, I can find a way to check my answer. I mean, I'm trying to show you how you check your answer on a test, folks. I mean, this is what you do. Huh? Some of you finished with about 25 minutes to spare. All right, here we go. All right. So this went really, really well during third hour. However, sometimes classes struggle with this, so I'm just going to try to tell you to lean in. First of all, do you know what this shape looks like? What does it look like? It's like a woo. Good. It's going to be shifted to the left one. And okay. So sometimes people are like, well, do we have to make a graph all the time, Mr. Gibbs? You guys, I'm making a graph because I want to help you understand it better. You don't have to make a graph for this problem, but I believe it's going to help you understand it better. Okay, so this graph starts, it has a starting point at negative 1, 4. Knowing that, what is going to be the start of the inverse? 4, negative 1. The inverse is going to start at 4, negative 1. Everybody agreed? Give myself some space here. So I already know that much about it. Let's solve. X equals 4 plus the root of y plus 1. What to do? X minus 4 equals the root of y plus 1. X minus 4 quantity squared is equal to y plus 1. Close. Yep. X minus 4 quantity squared is equal, or I'm sorry, minus 1. Minus 1 is equal to y. What shape does that make? It's parabola, and it's shifted. What's the vertex? Right, 4. Does that match with what I have there? Looks like we did it right, correct? Except we have a slight problem. At the beginning of class, we talked about a one-to-one function. You said no more parabolas. And yet, what do we have? We have a parabola. Look at this. This graph, and sorry, it's, like that, but then the red part, goes like that, right? So when we flip this over the line y equals x, we don't get those two shapes, do we? When we squared both sides, we created a problem. We don't want the red at all, do we? We only want the blue. So how do you give an answer that says we only want half of the graph? Well, you just say we want a specific domain. Well, no, I'm sorry. We don't want the left. We only want the right. We only want the blue. So the domain would be from? That's it. What that did for you is it took this red graph right there and it just got rid of it. And it said, I'm only talking about the blue part.
This feels like math problem doesn't work. Let's make it work.
Huh? Long division? I can give you all sorts of long division problems if you want. Okay, last two examples, A and B. Use the property of inverses in order to determine if f and g are inverses of each other. If we go back to our notes, we have one last piece to put in for our inverses. It's the test. And it's a beautiful test because it requires our knowledge of composition. Here we go. F of f inverse of x is equal to x. Also, f inverse of f of x is equal to x. So, in order to determine if functions are inverses, in order to show that they are inverses, you compose them together. You compose them together, okay? And it actually kind of makes sense. For example, can somebody tell me what is the inverse of multiplying by 2? What's the opposite of thing of multiplying by 2? Dividing by 2 or multiplying by a half, right? Would you guys agree that those are inverses of each other under multiplication? And what do you get when you multiply them? You get 1, right? And what if I have 3 and I want to add a number to it? What number would you add to 3? negative 3, that those are inverses of each other because you get 0, right? So what happens is when you do inverse operations of functions, they just cancel each other and they give you x. And we're going to show that that happens. And I know that that looks like magic, but that's what's happening. And we'll actually be using that operation moving forward. You'll see how easy this is, though. It says use the property of inverses to determine if they are inverses. And so we will simply just compose the functions together. So f composed of g. What do I do? I take this and I put it right there, right? And I get 3 times now, what's going to happen if you take 3 times this thing? What's going to happen to the 3's? They cancel, right? So you're going to be left with x plus 5 minus 5. Over 1, same thing, yep. Isn't that nice?
Yeah, because the 5's cancel out, right?
Very good, yep.
X equals X. I really hope this is
Now, you do have to compose them both ways because they are not commutative. No, what you're doing is you're showing that these. So if you were to do this, if you were to do y is equal to 3x minus 5, and you were to say I want to find its inverse, you would do x equals 3y minus 5, and then you would solve. And you should come up with this. But the true way to show that they are inverses isn't simply just to switch the x and y. It's to do composition. And when you do that, you should just come up with x. All right. Now what do I do? And I think that one of the best ways to do that is, again, just always show whatever you're substituting in, use parentheses. So I'm plugging that in for x, so I'm going to write as 3x minus 5, and then I have a plus 5, all over 3. So can somebody tell me what's the first piece that's going to simplify here? The 5's are going to go away. Good, I get 3x over 3, which is x. That's great.
Are we supposed to always come up with X?
Yes, if you didn't, either you made a mistake or they're not actually inverses.
Will we have problems with the
All the problems I'm going to give you will say show that they are inverses. Okay. If you just write x, I do not give you credit. Right, I'll show you what happens there. Last example. So this would be an example where everybody takes shortcuts on the test, okay? So they don't really understand, and they just write a bunch of gibberish, and they go X and box, and then I take points off. They're like, why are you such a jerk? I'm like, well, that's the way I was born. And so let me show you, and again, my encouragement is to use parentheses. It helps me to follow your work, and it helps you to organize your work. I'm going to take that and plug it in for that, right? So let's try to write this correctly. 1 over, then I have 1 over x minus 2. That's sitting where the x is, right? Then what do you have after that? Plus 2. Okay, so now that I can see it, what's the first thing that simplifies? Yeah, the 2's will cancel. Everybody agree? And I get 1 over x. Very good. Marissa says multiply by the reciprocal, and we get x. So therefore, those two are inverses of each other. Question?
Okay, wait, so why do the 2 cancel when you distribute them?
So it's not distribution as in multiplication, it's just plus. You can always take parentheses off when you see addition. If you see subtraction, you have to distribute through. And then our last one is g of f of x. So if I plug f in for g, Meaning I'm going to take this and put it there. Notice I have 1 over parentheses, 1 over x plus 2, minus 2. So when I'm watching your work, I want to make sure that you're plugging in correctly and simplifying the right thing first. People often just make stuff up and write stuff and then put x, but I follow your work. So what's the first thing that simplifies here? The 2's, or do I have to do the reciprocal first?
Hold on, why don't you get 1 over 1 over x?
So would you agree that 1 is 1 over 1?
Yeah.
And then I have 1 over x. And so when we divide, we can multiply by the reciprocal. And we get x over 1, which is x. So 1 over x plus 2 gives me
Wait, what did you just say?
this over that,
Gives you x.
x plus 2. And x plus 2 minus 2
Equals x.
equals x. Way to go. So they are inverses. You've shown it to be true. Excellent work. Good job. Oh,